different types of collisions. You've got elastic collision. This is where it's a bouncy collision and the total kinetic energy of the system is conserved. And completely inelastic collision. This is a sticky collision where the objects stick together. The total amount of kinetic energy of the system is lost. And an explosion. So an explosion is when one object becomes multiple smaller objects, and kinetic energy of the system is gained. Okay. Now, with all this said, okay, these characteristics of collisions and explosions is a condition determining if kinetic energy is conserved or not. Okay, this is not a condition for momentum. Momentum Okay, the momentum of the system is conserved in all of these, so long as you put the correct objects in your system. Okay, so if I say, oh, it's an elastic collision, don't think, oh my goodness, what happens to the momentum? It's like it's conserved. It's kinetic energy is the thing that is you're asking yourself, is it conserved or not? Okay. Now, just want to give a little disclaimer here. I'm checking a state standard in this slide right here. At a macro level, a real life level, there's no such thing as a truly elastic collision. That happens at microscopic levels, like little electrons. Okay, but real world, you're never going to get a totally perfectly elastic collision. But just like in physics, we can say we're going to ignore air resistance, or let's pretend this is a frictionless surface. We can pretend that this would be an elastic collision. Okay? You can pretend that this could be an elastic collision. Okay? So what I want you to do, and I'm going to prove to you why this isn't purely a elastic collision. Hold up a piece of paper, probably the lab that I just gave you, and smell it. Oh. Oops, sorry. What? I'm sorry. All right, so when these hit, what is that kinetic energy being turned into? Some of it's being turned into heat. Some of it's being turned into sound energy. Okay? Some of it's being converted in, or like it's still in kinetic, these things are still going to move. Does that make sense? So this would be an example of like showing that at a macro level, you're not going to get totally elastic collisions, but we can pretend that they are. Good with that? Okay. So all right. So I wanted to give you some exposure to this lab here. Okay. So you can find this on Canvas and follow along. It's probably going to be too small for you to read this. Maybe. Okay. So we've got cart A has no blocks. Cart B is weighted down with 2 blocks. Okay. We're going to give it a scenario in experiment 1 where 1 is moving fast this way, 2 is moving medium this way. What's going to happen when they collide? Okay, so get out your calculators, and I want you to answer these first couple questions here. Okay, you don't have to write down what you think, but have a mental image of what you think is going to happen afterwards. Mm-hmm. Thank you. So we've got a spring-loaded plunger. We're going to consider this an elastic collision when they hit. Okay. Sorry. So how do we do? You all right? Okay. Remember to incorporate direction. Okay. So you had a positive 0.5 and you had a negative 0.75. Add those together, you get negative 0.25. Good? Remember direction. So we're going to put both objects in the system, car A and B. Momentum will be conserved. Kinetic energy also will be conserved because elastic collision. What do you think is going to happen? Well, let's see what happens. This is coming in medium. This is coming in fast. They bounce off each other. Good with that? Okay. I want you to answer these next 5 questions. These, I'll just give you a heads up, are great test questions. I mean, just boom. Like choice A, choice B, same, can't be determined. Man, that's just like screams. I want to find this on the test. It's not intentional. Actually, go ahead and do the next 2 after that as well. Okay. How to do. Okay, I'm going to start going through these, explaining why these do what they do. Okay, which one experienced a greater change in velocity? A came in at fast, going in the positive, and came back medium in the negative. B came in medium in the negative and came back slow in the positive. Both bounced, but this one experienced a greater change in velocity. It's going fast this way and then medium the other way. This one, medium, and then slow. Good with that? Which experienced the greater force? Newton's third law has to be the same. Okay, that's a have to. Which one experienced that force for a greater period of time? Has to be the same. One can't touch the other one any longer than the other one's touching the other one back. I mean, that's kind of a consequence of Newton's third law as well. Do you remember the Volkswagen Bug and Mack truck collision experiment where we measured the force probes with the force probes, like it's the same force for the exact same amount of time. Okay, so because of that, they experienced the same change in momentum. Okay, so here's a factoid. During a collision, each object will always experience the same change in momentum because they experience the same force always for the same amount of time, always. Okay with that? Always experience the same change in momentum. Okay? Lots of concepts there. How are we doing with that? Experiment ones are laying a foundation. Okay. All right. This next part, remember how we made up numbers of how many pennies we put in kinetic energy and how many pennies we put in potential energy? This is going to have kind of a similar flavor of making up numbers. All right, so we had at the beginning values for the cart. So that's a positive 0.5 and a negative 0.75 to the left. Total momentum of the system was negative 0.25 to the left, right? So the total momentum of the system is still 0.25 to the left. This is where we make up numbers. Okay. These were all prescribed. I gave you those things and you figured those out. Okay. Now, here, the numbers we make up, there's two things that are limiting us. Number one, this needs to match what we see. When these came together, one went this way, the other one went that way. Okay, so A is going to the left, B is going to the right. Okay, and we also saw that A was going slower than it was originally. Okay, so I'm going to make up a number that's slower. I'm going to say say 0.3. Okay, this plus this has to give us this. That's the other constraint. That's the other relationship that we need to take into account. So this plus this gives us this. So what could that be? Has to be 0.05. Good with that? So I want to calculate the change in momentum of just cart A with these made up numbers. So A has a change in momentum final is negative 0.3 minus an initial positive 0.5. This has a change in momentum of negative 0.8. See how I did that? I want you to calculate the momentum, the change in momentum of cart B. What? Is that a coincidence? Well, prior to that, we said that the change in momentum of cart A should be the same as the change momentum of cart B because they experience the same force for the same amount of time. This is just a numerical, like, proof of concept. Yep, look at that. They both experience the same change in momentum. Okay. However, one was positive, one was negative. Okay. This is required for momentum to be conserved. So if we are looking at the whole system, there's no change in momentum. But if we're looking at the individual players in the system, A and B, cart A experienced a negative change of momentum of 0.8. Cart B experienced a positive change of 0.8. That enables us to say momentum is conserved because overall there is no change. So the players inside the system will experience the same change momentum. One's positive, one's negative, but overall there is no change. Does that make sense? How we doing? Long week. It's Tuesday. Okay. So looking at cart A, which way did cart A experience the force? To the right or to the left? Show me. Okay, left, negative direction. Huh, look at that. Negative change in momentum. Which way did cart B experience the force? To the right. Positive direction. Huh, that's funny. Okay, why is that true? Because the force causes a change in momentum. Okay, the force causes the change in momentum. Good with that? Okay. Experiment 1, we're laying down a foundation. There's a lot of concepts here. It's taking our time. Yeah. Next experiments will go faster. But any questions on this? My hope is this pseudo experiment brings things together. Okay. All right, experiment 2. We've got B is at rest, A is coming in like this. Once you calculate everything up to what will happen to the kinetic energy. Go. How do we do? Okay. So here's our experiment. Okay, do it again. Okay. In case you have a bad seat, can't see it. Okay. So go ahead and answer these two questions. How to do. Okay. A, going this way and then bounce back. Okay. This one started at rest and went that way. The fact that it bounced back, pretty good indicator. Experienced a greater change in velocity. Good with that? All right. I want you to fill out this momentum vector diagram. Based on what you see and constrained with the measurements. And then answer that final question. My numbers don't need to match your numbers, but that conclusion does need to match. How do we do? Is I going too fast? Like, my hope is you answered before I answered. That's what I'm going for. Okay, the total momentum of the system was to the right. You got something moving to the right, you got something moving to the left, but the total momentum of the system is to the right, then the thing going to the right has to have more momentum than the thing going to the left, because you add it together, it has to go to the right. Good there? This was the same question as the bowling ball with the golf ball hit from the worksheet and from the lab. Good with that? Okay. How we doing? Beside board. Okay. Experiment 3 is kind of lame. I'm just going to run through it. You don't have to do any measurements or write anything down. Just same mass coming in at same velocity. I'm going to tuck the plunger in so there's Velcro and they're going to stick together. Okay. That was an explosion. Not an inelastic collision. Stay. Okay. Kind of lame, but whatever. Good. Oh, yours didn't even hit. Yes. Okay, that was 3. Moving on. Experiment 4. Okay. So answer everything on this side. It doesn't matter. I'm not collecting this. I mean, you just saw it. This is just for your understanding. Getting bored? Yeah. All right. Okay. So how to do? Good to that. Yeah. Good question. They stick together, so it's an inelastic collision. Okay. So here's what this looks like. Coming together, same speed. Kind of lame. coming together, same speed. There's no, oh, there's Velcro. Good call. Coming together, same speed. Okay. So, answer the rest of those. How do we do on that one? So direction is kind of the key there. Okay. So here we have, what is it, 0.25 positive, 0.75 negative, 0.5 negative, 0.5 negative, and so when we answer these, both of these are going in the negative direction. You just need to make sure that A is less than B. Okay? Does this make sense? Why B has more momentum afterwards? Okay. Good with that? All right. Last experiment. This is just experiment number 5. This is looking at these two. They're connected, and we're going to do an explosion. They're at rest. What do you think is going to happen? I'm going to hit this trigger. They're going to, hit that trigger. Go to that. Explosion. All right, got a review worksheet due tomorrow.